So we started off with a single charge and learned what the electric field is that one charge creates around it. Then we went on to two charges, a dipole, a plus charge and a minus charge. And we learned what electric field a dipole makes. Well, then we could talk about three charges or four charges or five charges. But really, we need to generalize to some continuous distribution of charge, because very often the charged objects that we're talking about have charge distributed throughout their volume with some density. So we need to learn how to handle the possibility of some blob of charge. So this is some crazy shaped blob of charge density. And I want to ask the question, for some blob of charge, here's an arbitrary point P. What is the electric field at this point P that is created by this entire blob of charge? We're going to learn how to answer that question today. And what I'm going to do first is I'm going to walk through the logic of how to answer this question. I'm going to walk through the logic so that you understand where everything comes from, and so that you will be set up to analyze any blob you like. We will then go and do some specific calculations, and when we do specific calculations in full quantitative detail, we will not use crazy blobby shapes. We'll use simpler distributions. But I want to start in full generality and explain the logic of what we're going to do. So if I want to know what electric field does this blob make over here, I start by breaking my blob up into lots of little cells. So I cut up my charge density, my charge distribution, my blob into lots of cells. I won't draw them all, but I'll draw a bunch of them. Okay. And in a notation that we will not persist in using, I'm going to number these cells. So there's cell number 1, there's cell number 2, there's cell 3, there's cell 4, there's cell 5, there's cell 6, 7, 8, and there's cell 27, 28, 29, there's cell 30, 31, 32, 33, 34, there's cell 35, and there's cell 36. You get the idea. In each of these cells, there's a little bit of charge. There's some bit of charge coming from the blob of charge, but in each cell, there's some bit of charge. And I'm going to, again, in a notation that we will not use beyond today, I'm going to call the charge in this cell delta Q8. And I'm going to call the charge in this cell delta Q4. And I'm going to call the charge in this cell delta Q36. And what we need to do now is we need to figure out for each bit of charge in one cell, what electric field does it make here? And then we will have to vector add up all of those electric fields. You should already be able to tell from the way I've started to set this up that this is going to become an integral. And I want to explain that first with a much simpler calculation, which is I want to start by asking how do I relate all these little delta Q's to the total charge, capital Q. Capital Q is the charge of the whole blob. So how do I relate this charge, total Q, total charge, capital Q, to all the little delta Q's? Well, it's their sum. So capital Q is the sum on I of delta Qi. That is, this delta Q1 plus delta Q2 plus delta Q3, all the way up to delta Q36, delta Q37. It's the sum of all the delta Q's. But then you know that what we do next is we take a limit in which the cell size gets smaller and smaller and smaller. And this sum will become an integral. And in fact, it will become a triple integral, a three-dimensional or volume integral. And the limits on this volume integral are the edges of this blob, which I will try and represent here. So it's a pretty nasty three-dimensional volume integral. And what am I integrating over? Well, I'm adding up all the little dq's. And I'm going to refer to the charge inside a cell. Once I've taken the limit of the cell size getting arbitrarily small, the infinitesimal charge inside an infinitesimally small volume element I will call dq. And so the total charge q is a volume integral over the little dq's, and that is how I add up, which is to say integrate, all the charge in the little cells to get the total charge. And what I now need to do is to do something similar, but not for the total charge, but for the electric field at the point P. So what do I do? Well, first I ask, well, let's pick one of these cells. Let's pick cell 8 here. Let's ask, I've got a charge delta Q8 right here. How much electric field, what's the electric field made at the point P by the charge delta Q8? So we know how to do that. We use Coulomb's law, as we've learned how to do. I've got one bit of charge here, delta Q8, and that delta Q8 is separated from the point P by a vector that I will call R8. And this delta Q8 makes an electric field right here, pointing in this direction, and we will call the electric field made by the charge delta Q8, we will call E8. And what is E8? Well, E8, by Coulomb's law, is given by the fundamental constant in Coulomb's law times the charge, which is delta Q8, divided by this distance squared. This distance is the magnitude of R vector 8, so that's R8 squared. And now, if I stop here, I've got it all wrong because I've got a vector on this side. There's no vector here. So if you leave it like this, you lose points on your test. I need a vector here. What direction does this electric field point in? Well, it points in the R hat 8 unit vector direction. So right here, I need an R hat 8. Great. So that's the electric field at the point P caused by the charge in this cell. Now what about the charge in this cell? So let's consider now the charge in the 36th cell. There's my R36. That's going to make an E vector, which I will call E36. And E36 is given by K delta Q36 divided by R36 squared, R hat 36. So E36 points this way, E8 points this way, and I keep doing this. I do it for cell after cell after cell after cell after cell, and I get all of these vectors, and then I add them all up as vectors, and that will give me the electric field at the point P. And now I need to turn this from a finite sum written as the sum of lots of individual vectors numbered by an index 8 or an index 36. I need to turn this into an integral. And the way I do that is I'm going to need to do a little erasure first. So let me erase what we have here and replace my point P. Here's my P. And now I'm going to think of some generic infinitesimal cell right here. This is a generic infinitesimal cell. It's infinitesimal now. It's really, really tiny. And the charge in this generic cell is dq. And so the electric field caused by this infinitesimal cell at this point P, I'm going to refer to as dE. So this is the infinitesimal electric field at the point P caused by this infinitesimal bit of charge. And dE is given by K dq times this vector. This vector I'm just going to call R now. R is the vector from my bit of charge to the point P that I'm interested in. And what goes downstairs here is R squared, and what goes here is R hat being this vector. And then it's all just calculus from here, because the total electric field at the point P is then given by the volume integral over this crazy blob of dE. What does this mean? This means that as I'm doing this volume integral, I'm moving the location of my dq around to all possible points inside the blob. So as when I do a volume integral, I'm moving the dq that I'm talking about all the way through the blob. And for every spot that I pick, I'm going to have a different R and perhaps a different dq because the charge density might vary. But my final expression, which I will write down here, so my final expression for the electric field at the point P is given by the volume integral over the blob of k dq divided by r squared times r hat. And this is admittedly still a bit formal, but this is the expression for the electric field at a point P caused by some arbitrary blob of charge density over here. So what we're now ready to do is to learn how to actually turn this expression into a real integral that you can calculate and get a real answer for the electric field at the point P. I have to admit, though, that when we do that, we won't use blobs. The charge densities that we're going to look at will be simpler in their geometry. For example, we will consider a line of charge where the charge is distributed along a line with some charge density per unit length. We're going to consider a plane of charge where there's charge in a plane with some density of charge per unit area in the plane. And if I have a plane like this, I might want to know what the electric field is at a point up here. And then the third case that we'll consider is indeed a blob, but it won't be this blob. It will be a cylinder-shaped blob. So it will be a three-dimensional volume of charge, but it will have the shape of a cylinder so that we can actually do the integral. It will not be irregular in shape as here. But I wanted to begin by showing you the logic of the calculation for an arbitrary blob of charge, and here's the result.
Now, when we set up this abstract expression for how to find the electric field from a continuous source, the task now is to do that in a coordinate system. So let's choose a coordinate system for this problem. Now, one of the things that we can do is we can pick our origin anywhere we want. And I'll choose our origin at the end of the rod. And we'll choose I hat and j hat. The point P will have coordinates x and y. And now the crucial thing, though, is let's identify the quantities in here that we have to figure out. We have to figure out what that unit vector is. We have to figure out how much charge is on this little piece. We have to figure out what the distance is and the limits of the integral. So let's start with the dqs, because this is the one that's the trickiest. Notice that all of these dqs are a different distance from the origin. So what we need is our integration variable. So let's choose this distance here to be x prime, from there to there. So x prime is going to be the integration variable. Now, when setting up an infinitesimal element, we want to express that in terms of the integration variable. So the integration variable appears in two places. The size of this ds is also dx prime. And now we can write dqs, if you want to indicate that, it's equal to how much charge is on a length dx prime. Well, here we'll introduce a lambda, which is charge per length, because it was uniformly charged. And so this is lambda dx prime, which is q over L dx prime. That's our first item. Now, the unit vector r hat dqp, again, if we introduce an angle theta and an angle theta, our unit vector consists of a piece like this and a piece like that. And I'll just point out that this distance here, from here all the way out to there, is x. This is the distance x prime. So the key quantity in here will be x minus x prime is that distance. And this distance up here is simply y. That's what we need. So now we can express the unit vector r hat, which we've written as dq to p. That's cosine of theta I hat plus sine theta j hat. Now let me remind you that a unit vector has length 1. That's why there's nothing in front of the cosines and sines. And you can see in this picture that the cosine of theta is adjacent x minus x prime over hypotenuse, which we're calling r dqp. So we have the same type of result that we had for point charges. It's x minus x prime I hat over r dqp. And the sign is simply y j hat over r dqp. Now that distance is equal to the Pythagorean theorem, x minus x prime squared plus y squared to the 1/2 power, x minus x prime squared, y squared. And now we've got this piece, and we have that piece. And so we can set up our integral for the electric field of this source at the point P. It's the integral. I'll come to the limits in a moment. We have k dq is q over L dx prime. Downstairs, we have squared factor and one more. So it's cubed, just as we had before. So it's x minus x prime squared plus y squared to the 3/2 power. And the vector part in here is the x minus x prime I hat plus y j hat. Now, what you should notice here is that the integration variable is x prime. And what are we integrating x prime from? Remember, that's adding up all these contributions as we go out. So we're starting from the origin. So our first one is x prime equals 0. And we're integrating all the way out to x prime equals L. And that gives us the limits of our integral. Now, that's how we set up each piece. It's a little bit of work. And we've taken this abstract expression and expressed it in Cartesian coordinates. So we no longer need this abstract result. And what we want to understand now is this vector integral. Now, a vector integral, like any vector, has two components, one in the I hat direction and one in the j hat direction. And what that means is that, in fact, this is actually two separate integrals. That's all a vector integral is. Just do each component separately. So we have over here, we have x prime equals 0, x prime equals L. We're going to look at the x component first, kq lambda, x minus x prime I hat, divided by this denominator, x minus x prime squared plus y squared to 3/2. And now we have the other component, the j hat component. And again, that's an integral. X prime equals 0, x prime equals L, k q lambda. We only have the j hat component, so that's y j hat over x minus x prime squared plus y squared to the 3/2. And what we get here is a function, a vector field, due to the source at the field point x and y. And you give me the values of x and y. I do these integrals. I integrate out my integration variable x prime. Here it appears in the numerator and the denominator. Here the integration. Oh, we have to be careful. We've forgotten the dx prime. dx prime. And we have an x component and a y component. And those are integrals that you can calculate yourself as an exercise. And we'll show those integrals in another video, because those are integrals that appear again and again and again in this class.